Now to get the idea. So the next note, note number 6. During propagation, vibration occurs in all planes. During propagation, vibration occurs in all planes. In all planes. Depending on depending on the generation of EM waves, which can be polarized to a single plane using a polarizing filter. Once you're done, let me know. So just check out this video. You will understand what I mean by a polarization. So here, look, over here we have electromagnetic waves in several planes, but through this filter it will only allow the horizontal plane. So we only get the horizontal plane. So look, depending on which generates the electromagnetic wave, it can be in any plane. But if you want it in a single plane, then we can use a polarizing filter. So don't think that polarizing filter is something that's huge. Okay, that's a very small sheet. So if you rotate this sheet, then you can polarize. Let's say you rotate it to a certain angle, then you can polarize the red one. If you rotate to a certain angle, you can polarize the blue color one. Okay, it's something that's very small. It's not that huge in size. Let's see if we have any other video.
Once everything's perfectly organized, I'll start working on my thesis.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. But this way, what crazy wave I send, wave through.
Look,
No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer.
look
It's
how small it
polarizing
is.
up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
So you're clear with what is a polarizer. I think until I show this video, you still didn't have a good idea about polarization. Now I hope I'll have a better idea. Is that so? So I hope now this note number 5, 6 has to be clear. Note number 7. Note number 7. Now, what is producing these electromagnetic waves? Something has to produce these electromagnetic waves, right? So actually, it is the charges. When these charges, we can have 3 types of charges. I'm not talking about positive, negative, and neutral, okay? I'm not talking about that charge. I'm talking about their motion. They may be at rest. They are not moving. If they are not moving, we call them as electrostatic charge. Or we call them as a static electricity. Static electricity or electrostatic charge, whatever, static. They are not moving. When they are not moving, they will only produce electric field. They will only produce electric field. And then we have these charges moving. When these charges start to move, we call them as current. When these charges start to move, we call them as current. So in conductor, we have these charges moving. So we call them as electricity. So these charges are moving. So that is current. When we have a current, around it, we get a magnetic field as well as an electric field. So for current, we have electric field, let's say electric and magnetic field. Electric and magnetic field. But here, although they are moving, they move at a uniform velocity. Uniform velocity or uniform speed. Okay, they move at a uniform speed. Then we have the special type of charges. They are accelerating and decelerating. So these accelerating and decelerating charges, they produce electromagnetic wave. Okay, electromagnetic waves are produced by accelerating charges. or decelerating. Deceleration is also an acceleration, right? So EM waves are produced by accelerating charges. Okay, note this down. So you all have studied SHM, right? Simple harmonic motion. Okay, so you might get this idea. Have you seen these old antennas? In old antennas, we have these rods of different length, small, large, medium sized. So we have different length bars. Why do we actually have different length bars? The reason is simple. Now we have charges. These charges are going to accelerate and decelerate along this bar, along this length of the bar. So this is something additional, okay, what I am telling. So you will understand how these electromagnetic waves are produced. So depending on the length they have to accelerate and decelerate, the wave produced will differ, or the wave received will differ. This small bar will produce small waves or receive small waves. And these longer bars, they can produce EM waves that are having higher amplitude. So this bar, it allows for acceleration and deceleration of charges. Okay, that is something additional. If you want to know more about how antennas work, just Google it. Okay, with note number 7. Note number 8. Electromagnetic waves, they occur naturally and as well as they occur artificially. Okay. So Hannah, in note number 7, you will be studying about this static electricity in unit 6 and this one in unit 7. Okay. So there you will see that when charges are not moving, they are not moving. They are still at a certain point. Okay, they are still at a certain place. When they are still, they only produce a field called the electric field. They do not produce any other field. Okay. And if these charges start to move, we call them as current. When they start to move with uniform speed, we call them as current. So when there is current, there will be two types of field. There will be an electric field because we had charges. There will be an electric field. In addition to this electric field, we will get a magnetic field when they are moving with uniform speed. But when they start to accelerate or when they start to decelerate, when there's an acceleration and a deceleration, then they will produce electromagnetic waves in addition to electric field and magnetic field. Okay, Hannah. So that is what you have to understand. The point is electromagnetic waves are produced by accelerating charges. That is the only idea you have to know. Some of these points, when you study some other units, you will understand much better. Then note number 8. Electromagnetic waves occurs naturally and artificially. Where do they occur naturally? Sunlight and lightning. So these are natural. Artificially, light bulbs, X-ray tubes. There we produce them artificially. Note number 9. When light passes through glass, when light is passing through glass, all this time we thought that light is just passing through this block, right? Still we think that through glass, light will just pass through. But what actually happens is something quite different. What it does is, this medium, so now we have a wave that is approaching towards a certain medium. What they do is they absorb this energy and transmit the energy through this. After that, again they emit the energy. So that is how actually light passes through them. It is not just passing, instead it is absorbed and emitted. So next point, when EM waves pass through a medium, the particles absorb the wave and emits it back. Each and every medium will take different amount of time to absorb and emit. Depending on that, the speed of the wave through that medium will differ. Time taken for this process from material to material changes. Therefore, materials possesses different velocities for the propagation. Okay. During this, there's something special that happens. The wave, let's say it's of frequency f. The frequency of the wave is f. Here also it's f, the same frequency. Within the medium, also the frequency won't change. But lambda, the wavelength, lambda reduces, comma, speed reduces. Okay. Inside the material or inside the medium, the frequency is constant, lambda reduces, speed reduces. Once you have noted, let me know. Done. How about the others? Anna, Najima, and Natif. They will complete it. Yes, Imla. That means now we say that frequency is a property of the source. Now you have a bulb, okay? That bulb has a certain color. So this color is a property of this bulb. It won't change just because it is passing through glass. Now let's say this is glass. Just because this light is passing through glass, the color won't change. The color will remain the same after passing through the glass and when it comes out. But the time taken it to pass through this glass is different than it is passing in air. Okay, Imla, did you get the idea? So just like that, this frequency is a property that depends on the source. So just because it is going through a medium, it doesn't change. It remains a constant, but lambda will reduce. So note number no, subtopic, next subtopic, the electromagnetic spectrum. The electromagnetic spectrum. Stop. The electromagnetic spectrum. Now we know that this wave, the electromagnetic wave, it is in a huge range. You have waves that are very small in wavelength, and then we have waves that have very huge wavelength. And this is continuous. It is not a single wavelength. Now, if you have 100 nanometers, then you're going to have 101 nanometer. Even in between you will have this 100.5 nanometers and every possible wavelength. Okay, so it is not a single wave, it is a continuous range. If we put all of them together, then we get the electromagnetic spectrum. So in this electromagnetic spectrum, we can start with very huge wave, huge wavelength, and this wavelength then reduces. So try to draw it with the same amplitude. Now it's having a huge wavelength, then the wavelength reduces. Like that, okay? Just like this. So here we have a continuous wavelength. In this continuous wavelength, we can classify this wavelength into certain areas. So from a certain wavelength to a certain wavelength, we call them as radio waves. Then from that wavelength to 10 to the power 6 nanometers, we call them as microwaves. Similarly, we have infrared wave or infrared region. Next, we have a very small band that we call them as the visible region. Then we have got the ultraviolet, X-ray region, and gamma rays. So here, if you're finding it hard to draw this diagram, maybe you can get a printout and paste it nicely. So let's leave some space for this spectrum and let's write the note down. Okay. I know it's hard to draw. That's why I'm just leaving some space so you all can draw it beautifully later. Okay. So below that, let's write down the entire range of frequencies. The entire range of frequencies. Yeah, I will share. The entire range of frequencies of the electromagnetic wave is classified into various zones. First, we have the radio waves. What can you tell about the frequency? Its frequency is low frequency. But what can you tell about its wavelength? Wavelength is high. Low frequency, high wavelength. What are the examples for radio waves? For radio waves, we can further classify it as LV, MV, MW, SW, then FM, and FM waves, VHF, UHF. So when I said radio waves, what is the wave or what is the thing that came to your mind first? The radio, right? You got the idea of radio. But actually, is it only the radio? No, it is not. The radio that we know uses these FM waves. So these FM waves are used by radio stations. Then how about this VHF, UHF? Have you all heard about VHF, UHF? What does they stand for? VHF means very high frequency. UHF means ultra high frequency. Okay. What does this VHF, UHF relate to? Have you all heard about TV stations? They say tune to VHF 80 or tune to UHF 60. So this VHF, UHF, they are used by TV stations. Used by TV stations. So remember that TV waves are also a type of radio wave. The waves that are used by TV station are also a type of radio wave. Okay. Then what is this LW, MW, and SW? They stand for long wave, medium wave, and short wave. They are also used in communication, mainly in military and so on. Okay. Some of them are good for very long distance communication. Some of them are good for very short distance communication. So depending on the necessity, they use the relevant wave. Next type of wave, next region. So this is one region, the radio wave region. Next we have the microwave region. So microwaves. Where do we use microwaves? We use microwaves in micro ovens. Micro ovens. And we use them in satellite communication. The next region is the infrared region. Third region is the infrared region. Infrared waves. Where do we use infrared waves? We use these infrared waves in TV remotes. In TV remote in front. So this is the top wave. Here you have a small LED over here, right? A small LED. So that LED uses infrared waves. And we use them in night vision goggles. Night vision goggles. Imla, you're telling sonar. Okay, so sonar is ultrasonic. They use ultrasonic wave. Ultrasonic means that is sound wave. Ultrasonic is sound wave, and sound wave is a type of longitudinal wave. Okay, therefore, sonar is not it is not using electromagnetic wave. Sonar. Okay, I will just check about that. Imla says in sauna, a kind of therapy machine they use. So let's search about it, and I will let you know in the next class. Okay. Similar that we use for infrared or in microwaves. Okay, I will search about that. Thank you. So next,